Everyone again, and this is our last lecture in this mini lecture series on embodied patterns. So I'm really glad to be able to present my colleague and very good friend for many years, Michael Silver. The reason we somehow invited Michael within this particular lecture series that is dealing more with, let's say, science and computation in the context of design and architecture is because he's probably one of the most obsessive architects I know in terms of interests in these particular areas. He's reading scientists a lot, and we always have, over the years, these very active conversations about the role of computation within architecture and also some of these acute scientific ideas. And Michael is someone who even 10 years ago was really actively working with technology, working with fabrication, traveling through the country with his giant foam cutter. That's when I first time met him. He was living with a kind of, in his living space there was this machine, so he was always very much invested into testing the limits of or potentials of technology and fabrication. And in the past, he was a head of fabrication and digital media sequence at Yale. He also taught at GSD, at Pratt. Currently, he's heading also the digital media and fabrication at Cornell. So he has a very rich experience with this kind of fabrication technologies and in combination with computation. And he also edited a few interesting issues of architectural design. One was on mapping within digital media a few years ago, and then more recent one on programming cultures, tracking somehow younger generation of architects and designers and artists working with computation. So on that note, I thank Michael for coming.
Can everybody hear me okay? Yeah? All right, great. Well, thanks, Elisa, for inviting me here. It's really great to be in London for the first time in 20 years. It's changed quite a bit. Most of my traveling has been around the States looking at all sorts of strange factories and technologies in the heartland. And so I'm going to show you some of the crazy stuff I've found. But just also to start off, it was very exciting to see some of the student work yesterday. And I think one of the things that Elisa is really doing very well at is sort of pushing the paradigms of teaching and pedagogy. And I think one of the really interesting and promising directions in her class is the development of actually building fabrication machines and thinking about how to link programming and fabrication through the creation of the tools, which is something of a theme that I'll talk about too. I haven't seen that really pushed in any pedagogy in the schools or the practices that I've seen, so I really applaud that. I'm going to basically just talk about three particular topics tonight, and just briefly, this image on the board here showing some of the stuff that I've been looking at, everything from supercomputing to metaglass and smart materials, digital stone cutting, wire cutting machines, LiDAR. I'm not going to go into all of those. I'm going to really focus on three specific techniques, but I'm really interested not so much in trying to make architecture be about technology, but really looking at these technologies as a way to rethink architecture as an autonomous discipline with its own sort of skills and powers to affect human affairs. So I'm trying to really develop cogent applications for technology that allow you to develop ways of working in architecture on a different sort of dimension or level. So I'm going to take you through three sort of basic categories of technology, and then examples of unbuilt projects, and then one project that's sort of on hold because of the economy, but begin to really try to talk about the links specifically to architecture. So the three categories I'm going to look at is the development of applications. In other words, there's a shift in the discipline from the appropriation of computing tools to the development from the ground up of the tools themselves. I think this is a really significant shift in the discipline, the ability to write software and instead of trying to force certain sort of design ideas through prefabricated logics in software originally designed for making movies and other sort of aerospace applications. Second area I want to look at is actually trying trying to articulate another sort of level of digital fabrication, the next evolution in CNC technology beyond laser cutting and milling to a kind of exotic technology called fiber placement, actually quite ubiquitous in aerospace industry, the development of new kinds of materials. This is a pretty exciting world of new design potentials, and we'll look into that. And then the third category I'm going to look into is the potential of rethinking architecture and the way we work via increases in speed and computing power. In other words, the computers that you're going to be using over the next decade or two are going to increase in speed and power. Where do you look for ways of thinking about how that speed and power is going to affect your discipline? Well, you look at what the sciences are doing with supercomputers and high throughput simulation. So I'm going to kind of look at those three basic technological benchmarks and hopefully show you ways of producing architectural concepts out of these explorations. So the first thing I'm going to talk about is applications and development of applications. We just released Automation MP3 or AMP3. It's online. You can download it for free if you go to the Metropolis website. But this is the first complete standalone software developed from the ground up within a specific design project that we had. So in other words, we were designing a building. We were designing the software that made the building as well as try to realize that in physical three-dimensional space. So this software you can have for free. I'm not so much interested in you guys using it as much as just checking it out and getting inspired to develop your own software and to realize that developing these tools is really not hard. This program costs about $5,000 to make. So it's very cost effective, and to program these things it's not a really big mystery. You'll be surprised. So I'm going to talk about what it means to develop an application. I'm going to distinguish an application from scripting or applets or algorithms or genetic algorithms to say that an application is a full-blown tool. And the application idea, what is the idea of this application, is the same idea as searching for what is the idea of your building. And the idea of an application grows out of the process of trying to develop an architectural expression. In other words, a programmer with a programming degree is working with me, but I'm coming up with the ideas of what my software wants to be. I think at my generation, that's probably the best I can do. But with you guys, who are already starting to deal with codes and scripting, will probably combine programmer and architect into one package so that will produce a complete change in the way architecture is done. So I'm kind of in the transitional space where I need to work with a programmer, and I've worked with several programmers on this incredible talents, including my partner, Yi Pengqie, who's here tonight, and Chip Jansen, amazing painter and also a computer scientist. So again, the collaborative work with the programmer to develop the software from the ground up is actually a really rewarding experience. This particular program has everything in it. It has the 3D space, navigation tools, 3D modeler, and it has three basic engines that drive its construction. I'm going to talk about those three engines relative, or I call them modules, relative to the design of a particular approach to masonry architecture. My first module in the software is actually the generative module, which produces certain pattern logics in 3 dimensions. I took a very simple approach to the first module in developing the idea of patterns in masonry using simple programs. I was interested in simple programs simply because they kind of had an analogical connection to masonry constructions, ground up, discrete, binary. Seemed like these things operated like brick structures. So pretty basic idea. How could you then use simple programs to develop masonry structures, and how then would you translate that process into the building construction site? So the software is going to move from design idea or design schematic design through design development, through construction documents, and through construction, so that every time I need to move a step in the development of the application, I have to create a tool or a bridge to get me there. And being able to do that is actually really empowering, rather than having to force a piece of software which was never intended to do this to make these kinds of bridges. So this is the beautiful thing about being able to program from the ground up. So the first module is, again, talking about simple programs. I went with the very simple idea that a one-dimensional cellular automata is already a room. In other words, this CA that you see here, the left and right sides are continuous, right? It's a flat it's a two-dimensional space, but it's called technically a one-dimensional cellular automata. But since the left and right side are continuous, you can link them together, you have a cylinder, and therefore you have a room. So the idea of this looped wall that is constructed by a masonry became the basic idea of enclosing space. And then if you translate the black and white dots into, let's say, glass block and solid block, or hollow block and solid block, basically you have a wall that transmits light via fenestration pattern. And the first thing we tried to do is begin to set up a set of rules that would respond and develop a kind of programmatic container. In this case, we were working on the San Jose State Museum of Art competition in 2003. This was for a small museum in Silicon Valley, California, sort of an art school edition. Basically, this particular use of the pattern just involved the idea of a class 2 CA where the basic complex pattern, let me get a pointer, starts off fairly simple with these initial conditions, becomes very complex, and then just dies out and becomes blank space. That gives me now surfaces for display of artwork and storage, and then surfaces for the transmission of light into the offices, the galleries, the entryway cafe. So just now basically just trying to deal with how to get these self-organizing systems to develop into a kind of programmatic container. Also just developing that profile and where things meet up in terms of the interior became an interesting process of searching for patterns that had very precise fits to these existing programmatic conditions. And here you can see how that is worked out. Basically, there's 3 looped walls in the project, one exterior loop, one interior loop separating the atrium from the interior spaces of the cafe. There's a set of initial conditions, which are also, I'll talk a little bit about that, are the location of the concrete framing, and then basically, articulating a full-blown sort of a relationship between the skin and the interior plan. This shows the full 3-dimensional linking of those 3 loops around the stair, around the exterior wall, and then the atrium. That main space goes all the way up, and you can start to see the structure in the inside linked to the space. Here's some details. Labored over really developing patterns that turn the corner in a certain kind of way. Nothing seemingly random, but actually is very tightly controlled. This is an image of the building on the corner of the site near the student center on the right-hand side. And then the second module was an attempt to really think about structure. So since you're not really dealing with bearing walls anymore for a 6-story, 7-story building, you have to really deal with the idea of a concrete frame or a lightweight framing system. In this case, the second module was a structural calculator that started to integrate the patterning module with the structure. In this case, it was just based on a simple idea that with each of the initial conditions, you get a different wall type, right? Different patterning on that, and those initial conditions are linked into columns, and the columns then have different spacing, and therefore the beam depths change. So as you change the pattern in the initial condition, you change the structure. So that in a sense, the patterning of the skin is driving the structural frame and therefore developing a rhythm in space. So it's not now just a sort of ornate decorative container, but something that really permeates the structure and organization of the building. And this is just showing the atrium with that intersecting 3D space frame and the exterior simple program masonry envelope. So what we did is then after losing that competition, not even coming in 2nd or 3rd place, we actually got a commission to do a small project in Bangladesh. This is the site. This was one of my students got me this project. It's sort of on hold now because of the economy, but we got the plans approved by the city, and the client approved the project. Bangladesh is an interesting place, a really wonderful country. If you ever have a chance to visit, I recommend it. This is where Khan's assembly building is, a fantastic building. So this site's about a mile away from the assembly building. And this is, again, we use the same rule set, the same basic kind of patterning idea, but for a 6-story office block, only 5,000 square feet, very tiny. But again, trying to link intricate link between the enclosing skin and the structure and the interior program are coming together. Very hard to develop that. The project, instead of using glass block and solid block like the one we did in San Jose, where we use a hollow block and a solid block. So this is basically a really wet climate where you want to get air to move through the building, and you also want to protect from the bright sun. So again, we have spaces that are open and porous on the front. There's this two-story garden space on the corner, and then blanked out spaces to protect the workstations on each floor. And there's actually a slot of pattern all the way up on the back and on the side of the stair, which I'll show you in the next image, but that allows the air to flow through it, and so you get cross-ventilation. So developing and finding a pattern that fit all of those parameters was extremely difficult. And this is basically a fitness or a set of fitness diagrams that show you, well, in this particular case, we have a profile that needs to be no higher than the third floor. This one doesn't work. We need some light and air in the stairway. Well, this one works, but this doesn't. But this code, which took probably about a month to find, of just constantly changing the initial conditions, this actually has the ventilation screens for both sides of the building. This fits exactly within the kind of garden profile that's in the program, and there's actually now a required spacing in the beginning to allow you to drive 2 cars through the front of the facade. So moving those initial conditions, getting the profile right, getting sure you got blank space where you need it and porous space where you don't, was a process of intense crafting of the code and the initial conditions. So it's a highly responsive skin that looks sort of random, looks casual, but it's actually highly precise. Again, showing the same strategy of dealing with enclosing the space with a single looped wall. You have the vertical circulation. There's a glass sort of set of offices enclosed by the masonry screen, and that shows where the garden is on the ground floor. This is basically the ground floor, 2 cars you needed there, and then there's a small sort of garden space next to the core, adjacent to the core. So all of these things are now tightly interwoven, and this is all depending on the first two modules of the software, the genetic algorithm module and then the structural calculator. So the third module now, this is also just showing you kind of the 3D space there. And the inside of the wall from the interior. So the third module is now an attempt to develop some means of communicating that data to the site in an efficient way. One of the problems in Bangladesh is it's not a country where you can easily find a robotics brick stacking robot. And certainly if you were to ask Asimov, the Android Mason, to go stack some blocks, you'd probably have some hard time on the scaffolding. And also labor is really, skilled labor is really extensive. So it's not really a place where you have a lot of these high-tech devices, but you do have cell phones and MP3 players. Almost everybody has them. So our thought was to develop an application for the third module that would allow you to use a digital music player to sort of transmit via MP3s the information about this complex masonry structure to the mason working on the site, which turned out to be not such a hard problem. So the third module, if you see, and this is just a diagram of the software, the third module involves producing a set of audio files from the data. From the patterning language. So it's not really too difficult to actually do that. It turns out to make voice commands is fairly easy. Well, we tried, first of all, at Pratt to actually just try to manually compute these walls using a series of templates. It turned out that using the templates not only took more time than it would normally take if you looked at a drawing, but also the templates were extremely prone to error. So you needed then 2 people to check each other's work, so it doubled the amount of time that you required to actually build a wall. So literally trying to execute a cellular automata on site turned out to be completely useless or a waste of time. So this is sort of to explain why. So here's the 17th set of rules that you have to apply to 5 blocks in order to determine the state of 1. So every time you stack a block, you have to go through 17 templates. And this diagram shows that even if you make one little mistake, there's massive changes percolate through the system. So if you make a tiny error, it has enormous impact on the way the wall will come out. So you don't want to have errors. So we have to develop a compression routine that would take the information, get it to the site, but would be in a format that would reduce errors, and actually, if an error did occur, it would allow you to correct it without affecting the rest of the floors. So actually, this is what the Mason came up with. The guy who knows nothing about computing or computer programs, been dealing with Mason and training Masons for 30 years. He came up with this technique called run length encoding. And all it does is it says if you have, for instance, 5 white blocks in a row, you just indicate that as 5W. If you have 1 solid block, you say 1S. So this thing basically, all it does is it compresses that information into a format which reduces the likelihood of errors. And if an error does occur, it doesn't affect any of the other lines. So like if you do detect an error late in the construction process, you simply take that brick out and fix it. So this was a way of organizing the data that made sense from a Mason's point of view, not from a computational point of view, not from the abstract mathematics, but that mathematics being instantiated in a concrete situation using real Masons and real materials requires you to build and rethink the software idea and even the computational idea that was originally just the idea that, well, masonry structures can act like simple programs, but there's a difference. So that's when we developed a specific way of doing that by developing the MP3 player, which produces that zip file. So again, this project illustrates the development of the software tool. And again, you can go online. It'll generate a voice file. You can listen to it on your MP3. It's very boring. It's not musically interesting. But it does actually function as a way of expanding the idea of computer-aided fabrication beyond, let's say, milling and digital fabrication as we know it with laser cutting and 3D printers. And it does it within a specific culture. And through the process of programming, you can begin to really situate yourself in different functional and programmatic and cultural conditions. And you can really harness computing in ways which other disciplines really do more effectively than we do. And because we're kind of newcomers to that, the field. So the second project I want to look at is actually now moving from something more primitive like bricks to something extremely advanced called fiber placement technology. This is a really interesting material process that's becoming widespread in aerospace. The next Boeing airplane you'll be flying is entirely made out of this material, and this material is basically just reinforced plastic. Fiber placement, let's talk a little bit about composites. Basically, a thermoplastic or thermoset composite is just a plastic with reinforcing fibers embedded in it. And those fibers include Kevlar, boron, carbon fiber, glass, S-glass, E-glass, all kinds of anything that will basically take up the tensile strength of the material and bond it together in either a sandwich panel or basically just a compressed matrix. But laying down these materials and mass producing them is actually now done robotically. And the interesting thing about a composite is it's anisotropic, right? If you pull it, for instance, a carbon fiber in one direction, it's 300 KSI in tension. Steel, by comparison, is only 50 KSI. So you're talking about a huge increase in strength, tensile strength. And then also these materials are much, much lighter than metals. Most panels made out of aluminum, our composites would be 10 times lighter than an aluminum panel. So you got incredible lightness and incredible strength. And these are being fabricated on robotically controlled devices. So we're moving from, let's say, CNC and laser cutting where they're manipulating via the computer some old materials like wood and foam, metal. Here's a CNC device that produces materials with unprecedented strength to light properties. And they're being used extensively in aerospace. This also just shows Spaceship One. It's an entirely composite-based system. So just again, to talk a little bit about how these work, the fibers, again, take up the tension. The bonding matrix transmits the force between the fibers. Very high strength in tension. Not so great in compression, so you have to really work with the idea of tensegrity in your designs. But the nice thing about a fiber placement machine is that you can develop ways of putting the fibers to orient specifically to the force flows. And basically, the fiber placement machine is like a giant drawing machine, laying down strip by strip to pick up these forces. So you can begin to visualize or make clear some of the forces within a structure. This is some of the machines that go from different scales, from small parts to entire sort of building size components. This is the Ingersoll Rand machine. You can see here there's a taping head. It's laying down the fibers on a mandrel, which is a tool, some kind of mold. And what's really interesting about this thing is that you're not confined to geodetic control points. In other words, you don't have to do a faceted surface. You can do convex, concave, extremely complex curvatures with this technology. And you can see very close up the taping head laying down strand by strand the composite. So this is a really interesting computer control of the very sort of structural organization of the composite. So this is one of the machines for the project that we did. I haven't yet translated this into a full-blown architecture. So the project I'm going to show you is just for a new kind, developed a new kind of truss. So we're right now in the process of taking that structural idea and employing it at a larger scale. Some more thoughts on that. But basically, this is just showing you, let me turn that on, a fiber placement machine in action. You have, again, the tool here. You have a taping head down here with a nitrogen gas jet, basically melt bonding the fibers together using nitrogen so there's no oxygen bubbles, because you don't want any bubbles between the plies because that weakens the structure. And then up here you can see a little spool of material which you can swap out on the fly, stop the machine. You can add different fibers, combine them in different ways. You can have fibers that stop the light. You have fibers that transmit the light, glass and carbon fiber. But it's a fairly interesting technique which has hardly really been talked about in architecture at all. In fact, the company that I work with is, one of these factories that I just found in the middle of nowhere. I'm sure you don't know where Schenectady is. It's a crazy nowhere town upstate New York, but amazing factory with these amazing tools. And they do a lot of defense work, so I kind of go there trying to say, hey, maybe your karma will be better if you try to do something for peaceful purposes. So the thing that I'm after is trying to think, well, this is a new material with unprecedented structural properties. How can we really radicalize formal thinking? So the thing that I'm after is really a complete overhaul or overthrow of the one typology that would underlie the styles of architecture of the last 100 years from Sullivan to Gehry, and that would be the frame and the panel. In other words, most architectural compositions you see today are made out of some lightweight structure that takes the load and some non-load-bearing skin that is used to enclose thermally or spatially the exterior building. So how can we think about destroying that dialectic, overcoming that dialectic and opening it up to the idea of a structural membrane, a membrane that has everything in it, windows, structure, ultralight skin that does something that in itself is complete and organic rather than having to separate this out. So, all the way from the geodetic domes of Fuller to Mies, you're still dealing with this paradigm. So I'm going to show you how I think we can start to begin to formulate this transformation in this one seemingly inescapable typology of construction. And this is the Premier One business jet. This is the first all-composite passenger, small private plane scale passenger plane. It's built in Wichita, Kansas. It's a factory that, if you ever get a chance to come to the States, look me up. We'll take you there. It's amazing. What they're doing with materials and forms is totally outstrips architecture. But this is the Premier One. I lifted this 6-seat business jet up with my bare hands. It's so light. And this is a complete singular build without any kind of interior frame. The only bummer about this is that they have conventional ideas for windows. They fiber place the structure and then they water jet cut out the windows. I'm trying to think, well, if you can control the fibers, well, why not build the windows through the fibers, through the fiber orientation? But it's really amazing factory. This is a carbon fiber aircraft. I don't like the idea of using carbon fiber because it's oil-based. But there are other fibers like glass, and there's also other matrices that are soy-based that you can actually use to replace the the petroleum-based plastics. So beginning just to think about changing the paradigm of construction and therefore allowing you to change the form and tackling not just the ornament or the appearance of the building, but the very structure of the building. Just take Maison Domino, where you have this kind of free facade idea. No, the facade doesn't do any load-bearing work. Move it to a typical stress skin aircraft. The skin is actually in a structural synergy with the frame. You know, that's why they have so many little rivets that if you took a lot of rivets out, the thing would start to buckle. So you have the skin doing a lot of structural work in synergy with the frame. But in a fiber-placed part, in this case, it's called a squaricle. It's a test thing that goes from a square to a circle. The fibers themselves are doing the structural work without separating it out to a secondary supporting armature, just the way the Premier one is doing it. And so this is the key diagram, I think, that offers a solution, I think, or a set of promises about this technology. Just imagine a composite as the black being the fiber, the white being the binding agent. In this case, you have in A, you have basically one fiber-placed component. But with B, you have the white areas of the plastic extending between the fibers, becoming light-transmitting surfaces. So literally, the bonding agent extends between the fibers to become the window. So the window is an extension of the structure. So imagine this diagram is suggesting a kind of transparent reinforced concrete, where you would see, if you can imagine pouring a concrete that was completely transparent, you can adjust it to make windows, you can make it thick to create columns, and then you would see all the reinforcing in the building. Similar paradigm, but you wouldn't, with this, you wouldn't have to have a window that's placed in the structure as a separate system, and then you have the structural membrane doing all the work. Here, you can deal with the window, the aperture, unlike in the Premier one where you have to cut it out and then put a piece of glass in here. You can deal with the window as integral to the structure. I think that's a really key idea. So there's this moment of synergy and compressing everything into one material. So this is where we started. And again, another lesson in the power of software development. This project, we had no access to the software to run the machines because the software from the company is proprietary. It's their leading competitive edge. They keep it secret. They don't let anybody use it. So I had to have my programmer come in and work directly with the machine to write the code. The cool thing is we did it all in Java, and we did all of it in processing, believe it or not, because all you have to do eventually is produce G-code. So you can take processing, produce your taping patterns, and spit out G-code. That G-code goes right to the machine. So, and there's also a little bit tough times with mathematics because you have to have the control of the robot arm around the tool. So I needed a computer programmer who was also really good at math, which I was not. So this is where we started. First, we started with the idea of prioritizing the structural forces in a long span beam 100 feet. So this is basically 1, 2, 3, 4, 400 span, 100-foot long span beams with the fibers oriented to the maximal force loads. Turns out that to build that didn't really help us with natural light, and also it turned out that when you try to build one of these fiber-placed lines, and if you do it as a discrete motion, it takes a long time, especially if you're doing a lot of lines, to build a part because you have to start and stop the machine. Every time you start and stop the machine, you have to get a human being to come in there and actually physically locate the starting point for the thread. So you want to avoid stopping and starting machines. So we went all the way to these top two, which are basically just compressed spiral motions. So imagine you have a long tool, and you just have the machine constantly wrapping a thing. The machine, you can do one layer without ever stopping the machine. So we went with the idea of taking not just the priority of the structure, of trying to put material where you wanted and to loosen it up where you didn't, but also just use manufacturing as a way of sort of selecting which kind of patterns would be best. So in this case, we have these two patterns. And what's interesting here is if I compress the spiral enough, I can get solid wall to block out the light. And if I open up the spiral, I can get light to come through. And I can move that compression anywhere I want it. So I can not only respond to the structural ideas, but I can also start to respond to programmatic issues. So structure is not driving the process of form. It's a trilogy of relationships between manufacturing, programming, and structure. And that's where it gets interesting architecturally. So this was our idea of this kind of fiber-placed S-glass truss, where you have more dense fibers here to protect from the sun. You have more opening fibers where you want to let in light. That could switch between either side. Interesting thing is that when you have a lot of fibers compressed, you have a very good performance in the skin, but as soon as you begin to open up that fiber, you get a lot of surface buckling. So we had to figure out some way of satisfying the problem or solving the problem of the surface buckling without disturbing the priority of letting natural light go through it. And so what we did was actually quite interesting. All you have to do is add more layers where the pattern gets more open and decrease the amount of layers where the pattern gets tighter. So in section, you solve the problem of the buckling, and in plan, you solve the problem of the program of the light. In other words, I've reversed it here. I now have the light coming in towards the end and the light being blocked at the center, but I can easily reverse this. And this is just showing you now the kind of tool, the kind of mandrel, the kind of taping surface or mold that you're going to have to do this on. Will have to have a little bit of a taper, and so that taper reflects the structural idea in section. This is also just showing you now how that looks in 3 dimensions. You have a really interesting kind of light filtering thing here, and it gets solid there, starting to deal with issues of turning the corner. And then this just shows you, again, like program, this is not a design that's prioritized in terms only of structure, but also a program. So for instance, I could put dark space in the middle, and I can have light at the periphery, or I can reverse that. So I can push the apertures or the fenestration around to respond to programmatic ideas. So that's a key notion that this is not, let's say, a structural project per se, but one that integrates structure and the priorities of architecture simultaneously. And this is basically applied to a fellowship I had at Raphael Vignoli's office, where we just tried to think about a long span space to add between the project that they had in the office for a Cleveland Museum courtyard. And so this is basically a 100-foot span showing you some of the details. And the section, actually the section is smaller, 4 feet, than the actual steel sections that we're going to use. Plus, it's 10 times lighter. So they had something like 250,000 pounds for the steel and glass structure. This was down to something like 2,500. So you can literally helicopter in these things in one shot. And you saved all of the truckloads of materials and time that would have had to gone into building the steel structure. So just to diagram that out, if you take 3 roof sections, including mine, the Manila Museum by Renzo Piano requires a glass roof, a separate articulated space frame structure, and then these diffusers that then control the light below in the galleries. Kahn manages to reduce that to 2 by curving the beam and then putting in the reflector. Ours does it in one shot. Light, diffuser, wall, structure with one material. And the cool thing about this thing, there's a way to make it completely sustainable. And then you can make it sustainable on many levels, on the level of embodied energy and manufacturing, and also on the level of construction. So for instance, these diagrams show laser cutter, mill, filament winding, which is an older cousin of fiber placement machine, usually used when they didn't have a lot of powerful computers, so it's more of a mechanical process. Then small scale and large scale fiber placement. Since fiber placement is an additive process, you don't lose any material, right? So if you have a mill, you have to suck out a lot of material before you get to your part. Same with a laser cutter. No matter how you pack your files, you're still going to get a lot of scrap. Here, there's no loss of scrap because there's no loss of material because it's an additive process. And if you can get window, wall, structure into one surface, then you can eliminate all these different systems that have to come together on the site, and you can make one highly responsive programmatic element. So you save a lot of time and labor and energy on transporting the stuff in assembly. So there's a possibility of really beginning to develop a sustainable approach to these materials, where a notion of you can have complexity, but you can have it without excessiveness. In other words, you can do you can conserve energy, conserve mass and energy, but still have some degree of formal diversity in the project. So this was our first test part on this fiber placement machine. We used the spool of S-glass, so this is where the material is fed down to the taping head. These are the 2 nitrogen gas jets, and this is the mandrel that I had to build to tape on. Now, again, this is a fairly simple extrusion. Since it was our first test, we went with something simple, but there's no reason this mandrel can't be very contoured and complex and begin to thin up in section where you need it. and begin to develop more responsive shapes. This is just showing the programming for the machine. Each line is a normal, which is the taping head perpendicular to the surface being taped. This was all done on processing. So we didn't need any fancy software. I didn't need to use C++ or anything like that, which was AutoMason. This was just done really on the fly using a simple Java language in processing. Again, showing you the complexity. The hardest part was to turn that corner. It required a lot of mathematics, which I don't pretend to understand. This is showing the process of building the mandrel. The mandrel has to be made so that it could be disassembled and collapse inwardly, because when you wrap this thing, it becomes very tight and you can't pull the tool off. So this had to actually disassemble by removing these clips, and then the pieces fall in. This is showing the taping process, and then when it comes out of the machine, you have to actually douse it in some dry ice to cause the metal to shrink enough that you can pull out the part. And so here they're just extracting the part, which was a 10th scale model representation of the truss. Here's a close-up of the truss. Very strong. I mean, really lightweight. You can't really even bend this thing. It doesn't deflect. You can hold it on one end, and it won't even deform. It's pretty strong. So the last project I'm going to show and open up to questions is basically a project where rethinking the idea of speed and processing power via high-throughput simulation technologies. This is a picture of the Stormworm supercomputer, which is actually a networking supercomputer that links with other supercomputers to become a supercomputer. But again, infinitely expanding speeds are possible, and there's a whole discussion on how far you can go with that. And it seems that it is actually theoretically possible to go infinitely fast. But that's another story. Just to show you some of the effects of speed in the climate modeling world, starting in the 70s, maybe just being able to develop an atmosphere model, but current ones can take in account for vegetation, chemicals in the environment, ocean temperatures, et cetera. So the more speed you have, the more complex your models can expand, the more intricate and more precise your models become. Now, you're not going to have a model that's going to be exactly like the real thing, but you can get pretty near close. And this one is really interesting, under-talked about project called TransSims, developed at Los Alamos National Laboratory. This is seeds for a really interesting approach to urban design. But what this is a model of Albuquerque, New Mexico, and its vehicular traffic. What they did is they hooked up a supercomputer to the DOT's DOT's computer on census data for cars, like who owns them, how old are the cars, where do they go during the day, what their profession is. So literally it models all the motions of all the cars in the city, so that if you moved a bridge or added a traffic light, it will calculate the impact on the air quality. So here's an incredibly useful, sustainable, green modeling system that's networked to multiple databases, so that you can start to think strategically about urban design issues, but in a way that are both environmental, but also outstrip the possibilities of diagrams and simple plans. So I offer this idea as a challenge to the dominance of the diagram in architectural discourse. So a supercomputer model or a super simulation is not really a diagram. It's a kind of expansion of multiple diagrams ad infinitum. And here, this is, I think, the Earth simulation being simulator in Japan, where they're dealing with climate change. So you can go from urban scale to global scale with these kinds of models. So I think that's a really exciting shift. Now, I wasn't able to get access to a huge supercomputer. I had to deal with a small cluster machine, sort of like a rendering farm. It's called the Beowulf Cluster. And I wanted to really begin to start to deal with a complex site around Mont Saint-Michel. This is a project for a baptistry located in the tidal flat rather than on the island. So we wanted to really look at landscapes that we don't really consider suitable for building, because we really can't model them and can't really interact with them, because we still deal with fairly static modeling software. And again, here's amazing architectural site at low tide, a vast expanse of wet sand, but at high tide, completely surrounded by water. We wanted to put our building for a baptistry addition to this great medieval site. actually located in the bay. So we had to actually move away from this idea of a surface model to a voxel model. And voxels are basically just three-dimensional pixels packed together like a sugar cube, and you could model everything from simple platonic solids to more complex things like a vertebrae, or actually wave motions, or the interior of a body, or some kind of fluid space like some smoke. So you have this ability to work in depth rather than in just the 2.5D surface of a conventional modeling mesh. So this is just showing some of the first calculations we did. And the basic idea of this was that the computer programmer wrote up a sediment transport model for a small patch of the area. Again, this is a low-resolution model, but just really accounting for the depth of the water, the flow of the outflow of the tide, the mud and wet sand, the temperature of the water, etc. And I just handed him a series of architectural components, basically consisting of a deck with columns that float the deck above the flow. And every time I sent him one of these, we got a different result. So here you're just showing what the resulting landscape is as the tide rushes out to sea and the sediment flows around the columns, producing these different landscapes. These black pools represent puddles of water that become the font for the baptism. So literally, the interaction between the deck and the columns sculpts the land to become a kind of programmatic response. We like this one because the water came as close to the deck as possible so that the parishioner can gain access directly to it. The puddles here were too far away. So all I was doing was I sent him a model of this deck configuration, got this result, try to play with some other results, get an intuition of how I can shape the landscape, and kept on sending him models until I've got basically this arrangement, which was basically the landscape itself producing the function of the building. And this is just showing you the simulation in 2D. The two green dots are the columns intersecting the flow. So you can see here, this is the flowscape for the sediment transport model, and then here's the font slowly evolving. That's blue is the lowest point, so that's where the water would accumulate. So you would literally have to occupy this site or use this building according to the cycles of nature, because the puddles would eventually evaporate or the tide would return. This is showing you the basic structure of the building and the landscape. So here you have the two columns. Here's the deck above the flow, so everything flows underneath it, and it's only the columns. And sometimes the water does interact with the top of the deck to produce a certain kind of flow space, which you can't really model. You have to actually simulate it. And then this is just showing you the large trench, which is the font. And I usually show this project in relationship to it. This is an older project we did for Venice, Italy. This is a bridge near the Arsenal Canal, and you'll see the relationship to the baptistry. This is simply based on the idea that actually sinking the bridge into the water is better, because you can the distance between the water line and the bottom of a boat is often smaller clearance than the top of the water and the top of the boat. So literally just disappearing the span into the water makes it easier to allow clearance for passing vessels. And it's also at least a very little intrusion upon the historical context of the site. This is just showing the model we made. It's actually casted silver fittings. It's a kind of crazy model with a nickel-etched, acid-etched nickel silver. It's pretty, and it actually moves. All of this is all figured out. And it's showing you basically the construction of the bridge in a factory, loading it on a truck, dumping it on a barge, installing it in the site, and then in its submerged position, the building reproduces the conditions of the site prior to construction. So literally, by sinking into the bridge, it functions by letting the boats come by, and then it reappears to become a bridge. But this idea of like erasing the new intervention in the city to respect the existing context sort of works with the idea of Venice. But this relates to the baptistry, because at high tide, the baptistry also completely disappears, and this site becomes the biggest building in the world, an infinite font, all the way to the coast of the United States. So you have basically this idea that this is an architecture without architecture. But the other thing that's really interesting is that the function for the building is both here and is both there and not there simultaneously. So you can say, well, is this really architecture? But you can also say, yes, this is actually architecture. This is actually a baptistry. So The idea here also of questioning the idea of what's real in terms of the function of the building is called into question. Also, right here you have the idea that, you know, the function is infinitely there and not there, so there's actually no space, because if you go wherever you go, there's still architecture. So I'll end right there and to take any questions if anybody has any.
Thank you, Michael, very much for this lecture. So, any questions?
Well, thank you very much. Appreciate it.